Well, Roz, at the start of Unit 7, what we do is we take our ideas of sequence and series and we're going to apply them to a very popular application, which is finance. We're going to dive right into these terms here, though. I'm going to be completing the worksheet 7.1.1, which may have been done in class, but this will give us a chance to discuss it for anyone who wasn't able to attend the lesson. So imagine that we have $700. We're investing it at 9% per annum, or just per year. It's a fancy way of saying per year. Financial people sometimes need to sound smarter than other people, so they invent words like this. Simple interest for 10 years. Okay, simple interest. So basically we're asked, what happens to interest earned in simple interest situation? Well, let me tell you. First off, in these charts, you're often going to see me create a chart that has year 0 here, and that throws a couple of students off. You want to think of this as being the end of year 0. So here, this will be the end of year 5. The end of year 0 then is like the beginning of year 1. It just sort of establishes our beginning position. Let's make sure this principal is measured in dollars, interest in dollars, and the amount is measured in dollars as well. So we start off with $700 principal. We earn 0 interest at the beginning, so our total amount is 700. Seems like a bit of a waste of a column, but if we were doing this in a spreadsheet, you'd see that we could apply a formula and drag it down. So get used to seeing that. All right. At the for year 1, we begin with this principal. So I would copy this cell here and paste it there. And the interest that I get in simple interest is going to be 9% of 700. Now I guess we could do this probably by eye and say 10% is going to be, 1% would be 7. So 9% should be $63. 700 times 0.09. Yeah, $63. So here's what happens in simple interest. There's a couple of ways of thinking about it. One way is either thinking about the interest is held elsewhere. Interest is held elsewhere. Right, so it's not reinvested in the fund. If we were to cash out at the end of the first year, we would have $763. But in a simple interest situation, for the second year, we are only earning interest on $700. Okay. Now, there's another way of thinking about this, but I think I might wait until the end to sort of just show you how quickly this can be calculated. This portion of the chart isn't going to be difficult, though, because since in simple interest, our principal doesn't change, our interest also shouldn't change down to $63. It should stay constant, or $60. It should stay constant at $63. And then what you end up doing is just adding $63 each time, and that should sound familiar. There's some sort of number here that you are adding constantly. Sorry, my calculator's just not cooperating. 763 plus 63. It's going to be 826 plus 63 is going to be $889 plus 63 is going to be $952 plus 63 is going to be $1,015. Okay. And we shouldn't get too excited by these investments. We're not going to get rich investing $700 for 5 years at 9% per annum, but it is money that we wouldn't have had elsewhere. If I just put $700 under my mattress, at the end of 5 years, I would have had $700. Some people would consider, if you're able to get an investment at 9% interest, that you're actually losing $315 here by not taking advantage of the interest. It's an opinion, I suppose. So the value of the interest each year, it does not change, remains constant. And so if we graph the total amount versus the year, total amount versus year here, we'll use capital A for amount and maybe T for time in years here. We begin here at 700 and we jump up by $63 each year, which means that we see linear growth. So the other way of performing this calculation, which you likely saw if you look at your textbook or if you were present for the lesson, is you can think of the interest isn't even calculated until the end. Interest is not calculated until, let's use a fancy word so we sound like we're finance people, maturity. Very grown-up word. Okay. So to perform this jump without having to use a chart, because we definitely don't want to use a chart. We could do this with Google Sheets, and that'd be great, but we should be able to do this with a scientific calculator. We should be able to say that the interest is dependent on our principal, how much we invest. It's dependent on our rate as well. I need to multiply my principal by my rate. That was the 700 times 0.09. But I want to do that 5 times. So I take my principal multiplied by my simple annual interest rate multiplied by the number of years. And watch what happens if we do $700 earning 9% interest 5 times. Well, wouldn't I just get 63? Let's show it on the screen. Times 0.09, $63 5 times, or the $315 that we mentioned. Yes, we would. To determine our final amount in a lump sum, which means we're not putting money in from outside or we're not taking money out from inside. Our final amount is going to be our principal plus our interest. This is a formula that, I think both of these formulas, you don't need to write down on a formula sheet. You're not going to be given them on the formula sheet. You don't need to worry about memorizing them. They should make sense. Talk through this one with me. If we started with $700 and we earned $315 interest, then our final amount should be what we started with plus what has gone up, the growth, I suppose. Some people do take exception to me using the word earn here, because really, what have we done to earn this money? Your answer is going to depend on your philosophy here. A capitalist would say, well, you gave up all of the benefits of having the $700. Therefore, the bank or whoever is borrowing money from you owes you money for the benefits that you could have had, where people of other religions and different financial philosophies would say, yeah, you didn't earn it. This is just a way for rich people to get richer. So those are probably the two extremes, I suppose, of philosophy. Maybe you're in the middle somewhere. Okay. So let's look at something called compounding here. In question number 2, we say $700 is invested at 9% per annum annually for 5 years. Everything looks about the same, except we have this word compounded. It says in a compound interest situation, the interest earned is reinvested towards the principal. So we don't just take this interest and put it somewhere else and don't let it grow. We're actually going to reinvest it towards our principal. So our principal is going to grow. And this means that we can't, it's not as easy, let's say, to jump to the end and just perform one calculation. We'll figure out how to do that very quickly. So at the end of year 0, we have a principal of $700. We have earned $0 interest. Our total amount is going to be $700. I copy this and paste it there. So at the beginning of year 0, or for year 1, sorry, I have $700. I earn 9% interest on that, so that's going to be 700 times 0.09, which is going to be the same as the column above, and $63. And my amount at the first year is also going to be the same, 700 plus $63. So sorry, if I was doing this in a spreadsheet, I would have typed this in. This would be just put in a 0. This cell would be that cell plus that cell. I copy the cell and I paste it there. Or I say I want this cell to be the same as that cell. This one I do 700 times 0.09, and I put it there, and then I perform the same operation and say I want this cell here, your principal for the start of the second year, to be your amount for the end of the first year. So this interest is calculated. It's grown, the principal has grown to $763. We reinvest that. And now if we're investing, this is good news, because now we're earning interest on interest. Again, the capitalists are celebrating here. The thing is that I don't want to get too much into the philosophy, but imagine this being a loan. So you've borrowed $700, and then at the end of the first year, you now owe $763. Well, guess what? During the second year, they're not just going to charge you $63 interest. They're going to say you now owe us $763, so we're going to calculate interest on the interest, and then interest on the interest on the interest. So it's a situation that rewards the loaner and kind of penalizes the borrower. Okay. Notice how our interest has gone up here, and then my total amount, I'm going to do $763 plus $68.67. Again, in a spreadsheet, I could just say make this cell, plus that cell. And once I have my cells programmed, I can just drag them down and have the formula apply and drag it down as far as I need to. Okay, $831.67 at 9% interest. I'm going to round this off to about $74.85. Add that to $831.67, and we get $906.52, which becomes our new principal. Calculate interest on that. $81.59. Add that on. 906 plus 52. $988 and about 11 cents. $988.11 times 0.09. $88.93. So notice our interest is growing, which means our total amount is growing faster. 0.01. Perhaps you've heard someone, maybe your math teacher, say, you know, something like, oh, if you make a mistake and then you lie about it, you just compound the situation. You just make it more complicated, worse, I suppose. I don't use the word compound in a positive sense outside of finance very often. Right. The value of the interest earned each year, it is growing. It's not constant. If we sketch a graph of this is going to be a very rough sketch, but you can do it a little bit more accurately. Say with a spreadsheet, amount versus time, we're going up a little bit and then up by a little bit more and then up by a little bit more and then up by a little bit more. And you might just want to trust me on this one. That is it. It is going to be exponential growth. Okay. We need to turn to the back side now to actually sort of see what's happening here as well. In question number 2, we're sort of treating it as a sequence. Let me get the numbers down here real quick. I'm going to write them down on another piece of paper. 700, 763, 831.67. I wonder if that's enough. Oh yeah, that's exactly what I'm asked to do. 700, 763, 831.67. Wonder if I still have them on my calculator, if I can read them off. I cannot. 906, 52, 988, 11, 1077.04. The fact that I'm rounding these numbers off is going to cause a bit of an issue, but I don't think I was rounding off for this third calculation. 0.52, 988.11, 1077.03. Sorry, there you go. The type of sequence, well, our simple interest, the sequence is definitely arithmetic because we're going up by 63 each time. We're not going up by 63 each time, and I can tell that because I'm getting some decimals here. So let's test our second hypothesis. What happens if we do our second term divided by our first term, or 763 divided by 700? You should be able to predict what this number is going to be. Divided by 700. That's 1.09. That's a 100% increase plus a 9% increase, or a 9% increase on, that's 100% of what we have plus 9% increase, so a 9% increase on the total. Term 3 divided by term 2 is going to be 831.67 divided by 763. 831.67 divided by 763. 1.09. Now approximations would happen because I was rounding these off to the nearest cent right there. Okay, so actually we have done this next question right here. Our common ratio is 1.09. That is our unit 6 ratio, not our unit 7 simple interest rate. That makes this a geometric sequence. If we take our formula for a geometric sequence, T sub n equals a times r to the exponent n minus 1. and we replace this with our purpose in this application, we can get that the amount of a compound interest lump sum is going to be your principal multiplied by 1 plus lowercase I, which we're going to call your compounded interest rate to the exponent n. And notice that there are a couple of differences here. Let's switch colors. A is your amount. Unlike the simple interest formula, you don't calculate your interest initially. In compound interest situations, you calculate the amount. P is your principal. Principal. Lowercase I is your compounded interest rate. We're not going to talk about that until lesson 7.2. And that's your interest rate per compounding period. And n is the number of periods. In today's lessons, we keep the compounding frequency to be the same as, or sorry, to be the length of 1 year. So the number of years should be equal to the number of compounding periods. Like I said, that changes in 7.2. Okay. So yeah, it means that we can basically treat these as sequence and series questions. And that's one option instead of memorizing totally new formulas here. Let's try it out. It says use your expression to answer the following questions without a chart, because I don't want to have to do 12 repeated calculations. I don't want to have to find a spreadsheet and use it. It says find the amount of $1,200 invested at 7% per annum. That's normally my annual interest rate because it's compounded annually. That's also my annual interest rate. 12 years is my length of time, but because we're compounding annually, that's also the number of compounding periods. This will make more sense in 7.2. So the amount is going to be this $1,200. Now, what we definitely don't want to do is what we did on the chart. You don't want to have to calculate 7%, then add it on, then calculate 7%, then add it on, and do that 12 times. What you're actually doing, first off, is you're saying, I'm going to calculate 7% and add it on in one step by multiplying by 1.07. I hope you've seen this done in a grade 9 class, where if you're calculating a final value with tax, you don't need to multiply by 0.13 to calculate the tax and then add it on. You can just multiply by 1.13, and that will calculate the tax and add it on to the original price. And now, this would give me the amount at the end of the first year. If I multiply it by another 1.07, I would get the amount at the end of the second year. Instead of doing 12 calculations, let's use an exponent to create a power to perform those 12 calculations for us. And we should be able to read from left to right and just type this in here. Let's see, we have 1,200 times 1 plus 0.07. I might do 1.07 later to help my calculator out, to the exponent 12. And it spits out $2,702.63. Okay. You can get more growth with compound interest because you're calculating interest and you're growing more often. It compounds, is what we say. Now just read questions carefully because sometimes you're asked for different things. Here, $700 is invested at 4% per annum. It's compounded annually, so that's my annual interest rate for 9 years. So I'm compounding 9 times. I was asked how much interest is calculated. Now, we could try inventing a new formula just for the interest from compound interest, but it's probably safest just to start by calculating your amount. $500 growing at 4% per annum for 9 years is going to give me 500 bracket 1.04 to the exponent 9, $711.66. Well, how much of that is interest? 500 of it is principal. If I say my final amount should be my principal plus my interest, it should make sense that my interest is the difference between my amount and my principal. Yeah, this is not another formula we need to memorize. It's just a simple rearrangement of this or an application of logic. So we ended with $711.66, but we started with $500. Why are these numbers different? What is the name for this difference? Well, this difference is called the interest. This is the time value of money. So I'll just announce to my reader, this is what I'm doing. I'm doing my amount minus my principal, and there's my interest. Okay. And question 8, let's just compare simple versus compound. How much more is earned? We should be able to look at a difference in the amounts. The challenge here might be if we're going to do simple interest, then we usually just start by calculating the interest, and that would be the principal of $850, earning 5.3%. Careful with decimal percents, it's a common mistake for students. For 8 years, 850 times 0.053 times 8. That seems high. Let me try that again. 850 times 0.053 times 8. Okay. $360.40. Let's switch this to an amount then and say the amount for simple interest is going to be $850 that we start with, plus $360.40 that we end with, plus 850. So we're finishing with $1,210.40 in simple. But if we compound it, instead of calculating interest just one time at the end and adding up 8 years worth of interest without compounding, every time that I calculate interest, it increases my principal, which makes my principal grow, which makes my interest grow, which makes my amount grow as well. Oops. 5.3 compounded 8 times. Okay, we're talking about the difference between multiplying by 8 and raising to the exponent 8. It's not quite as simple as that, but that's in effect why things are growing faster. 850 times 1.053 to the exponent 8. Yeah, now it's not a huge difference because our principal is small, the interest rate is mediocre, and the length of time is decent, I suppose. But these small differences, if we're talking about hundreds of thousands of dollars, these small differences do add up. Our difference then is going to be the bigger number minus the smaller number. It's always a good idea, this shouldn't sound new, to label what you're doing and then show the operation that you're performing, not just write down answers on your page. Okay, there's a difference of $74.43. Okay. You sometimes get a kind of sarcastic student who like whistles at this point or says, whoa, and says, oh, that's not that big of a deal. Well, then all right, then give me $74.43 if it's not that big of a deal. And no one's taken me up on the offer because it's a significant amount of money. And if I have the chance of choosing between simple or compound interest, as an investor, I would choose compound. This again does not work to the advantage of the lender. Okay, try it out. We'll talk more about compound interest in 7.2.